This is a little bit of review. So some review here as far as stuff that you would have been coming across, perhaps in a previous video lecture. This isn't really a question I would ever ask in an exam. This question here, but why do you think? Why are the oceans salty? Why are they so pissed off? I mean, why are they salty? Why do they actually have a salty, you take, I don't know what I just did there, but you let the water in the ocean, it's salty. Why is that the case? Any idea why? The White River, it ain't salty.
Well, I don't know if this has anything to do with it, but the rain cycle.
Yes, and so the rain cycle explains it for sure. Want to keep going, or?
I'm done.
Okay, so that helps. That gets us going. Yeah.
I would say, like, White River, doesn't it, not necessarily get filtered, but it kind of goes, it's not just open bodied waters. It's kind of like closed off more so.
Oh, that's the first thing. When you say
like comparison, like White River into actual ocean.
Right.
More the ocean is more. It's not as controlled by man as like the river could be. Could be altered more so.
But I like what you said there at the beginning. That's probably one word. Yeah. So I like what you said. The ocean is kind of a stable body. Yeah, we have waves and all of that. We look at rivers. Rivers are always carrying sediment, and they're dumping that sediment into oceans. And so what happens is over time, that salt, over millions and millions of years, is essentially weathering and erosion, has picked up that salt from the land, from actual the inner part of the United States, and then essentially the rivers take that salt and then dump it out into an ocean. And so the rain cycle, the hydrologic cycle, all of that, so as rain, it pours down and then causes rivers to flow. What ends up happening is the rivers then flow into the ocean, and then we get what happening? Evaporation. And when evaporation happens, that's when the salt stays behind. The salt does not continue on. What happens is the water vapor continues on. We get the whole hydrologic cycle and all of that. But essentially, the salt stays in the oceans. And that makes sense because it doesn't have anywhere to take it. It doesn't have any farther places to go. It can only go to the ocean. Essentially, the lowest line, sea level, where everything comes to the surface of the water. So here, the surface of the water is, and the ocean is where we have this process occurring. And so in the ocean is where we have the erosioning and weathering, dumping that salt, among a whole lot of other stuff as well. I mean, it's not just salt. But over time, that salt remains. And so this is what I'm talking about. Millions and millions of years of this occurring is why the oceans are salty. All right. So here we have what would have been the Math Quiz 3 key, or a good part of it. So here we have all of our rivers. And so I'm not going to go through the rivers. Why not? We will go through the rivers. And so here we've got what river? The Missouri River. So the Missouri River, if you know, where does the Missouri River start? It starts actually in the Rocky Mountains. And so everything in its path, all the various sediments that collect all the way up here in the Rockies, eventually make it all the way down here to our good friends in New Orleans and the Gulf of Mexico. So essentially this river here, although it's way out there in the Rockies, it actually drains down into the Gulf of Mexico, which is also the same spot where our White River ends up draining to. So this our river right out here, right out there, goes eventually to the same spot. And so this kind of shows you how big this whole entire, what we call a watershed or drainage basin is, the largest in the United States. The one that comprises the Missouri River, the Mississippi River, and the Ohio. So here we also have the Appalachian Mountains. So you look at the Appalachian Mountains, the Ohio River is key to bringing that sediment that's over time, the Appalachian Mountains have been worn down, they're now little hills. Well, what's happened is that sediment's been removed and carried by rivers and eventually dumped out here into the Gulf of Mexico. And so what we have is this big, huge drainage basin. So what these are is these represent drainage divides. So in other words, everything inside this basin flows in one direction here, eventually making it to the Gulf of Mexico, which of course filters into the Atlantic Ocean. But then we also have these other drainage basins. And so everything on this side of this particular red line, everything flows to the Atlantic, not to the Gulf of Mexico. And finally, you look at northern Indiana. Northern Indiana, we're talking about the northern, let's say 10th or maybe 9th of the state, actually is part of the drainage basin that goes towards the Atlantic via the Great Lakes and the St. Lawrence Seaway in that way. So here kind of gives you an idea as far as the drainage patterns, and of course, way out here we got other patterns. United States, this is a question that is, I remember it being asked once at trivia about 15 years ago when I first was playing trivia at a bar, and one of the questions was how many oceans do rivers in the United States drain into? And everyone put, Atlantic and Pacific, because of this, these rivers flow into the Atlantic, these rivers flow to the Pacific, but it's actually 3 different oceans, the third being the Arctic Ocean. So the Arctic Ocean up here in northern Dakota, the rivers actually flow towards the North Pole. And that also debunks a myth that all rivers, no rivers can go north. Actually, rivers can go north. I don't know where that myth came from, but that's quite false. Anyway, so all this gets us to understanding a little bit as far as the runoff that eventually heads to the oceans and creates salty oceans. But why is the Great Salt Lake so salty? Here's its place right there. It's the middle of a continent. Why the hell is it salty?
Wasn't it originally underwater?
It was underwater. So you could also say that about Indiana. Indiana was also underwater.
Limestone.
So they have limestone there, but it's not like ours. It's more of a sandy limestone. Ours is more of a rock. Okay, I like that idea. But what else might be a reason why the Great Salt Lake is so salty?
Is there a river that drains into it?
Yeah, there's a river that drains into it. In fact, all the rivers in the area drain into this particular area. So this all used to be a big lake bed, big huge lake that dominated this entire state of Utah. It was before all the Mormons got there. It was flooded with this big huge inland sea, and over time that inland sea is drying up. So essentially, the same idea we heard earlier regarding how rivers take sediment to oceans. And the oceans have nowhere for that to be drained. It can't just go, through the stemosphere. It's pretty much the only place they got to go. In the case of this particular area of the country, it's a big bowl. It's a big depression. And so at the bottom of that big bowl is essentially the Great Salt Lake. And so what we have here is we don't have a river to take that salty water anywhere else. And so over time, that salty water accumulates because it has no river to take it somewhere else where it can then dump that sediment into an ocean. So over time, the Great Salt Lake, it's also getting saltier. But that's for a few different reasons, and I'm not going to go into all of that. That's the Great Salt Lake. It kind of, once again, ties into some big picture stuff that we talked about in the rivers and in the weathering and erosion stuff. Indiana has 36,000 miles of rivers. Where does the water come from? Lake Michigan. Lake Michigan it's not sea level, but it's one of the lowest areas of sea level in Indiana, so it wouldn't be able to go uphill.
Where would be the Wabash?
The Wabash. Okay, so we have the Wabash. But where does the water that fills the Wabash come from? Groundwater. So we have groundwater. So there's a little bit of groundwater that can kind of pop up as a spring, for example. But 99% of it comes from rain. Comes from the sky. Comes from up above us. Comes from the heavens, let's say. So rain. So we think about our rivers. What's key to creating the rivers, creating the flow of water, is the precipitation. So this kind of also dovetails nicely with when we look at climate regions. And so we are more humid. We're more of a humid area of the country. And so subsequently we get a lot of rain. And so then you add to that fact we're in the mid-latitude cyclonic area. We're going to get the low pressures, the high pressures, the changing weather conditions, the warm fronts, the cold fronts, and all of that. Throw in the fact we've got, of course, the convection storms that happen in the summertime. All of that combined helps to explain where that water comes from. That's helping all those dead bodies in the White River flow down slope towards the southern part of the state. Anyway, so here's a map that shows Indiana's rivers. So this is something you probably would have already came across in the previous discussion, but the Indiana rivers, we can see how they generally flow from the northeast to the southwest. And that makes sense. We look at where the highest point in the state is, it's where that red dot is. You look where the lowest point in the state is, it's where the green dot is. And so for the most part, everything goes from high to low. And that makes sense because water, of course, is going to go downhill. So here's a color image of what you see there. It's black and white. It's hard to see. But nonetheless, what this shows is that places that are white or brown in color are at higher elevation than places that are green or turquoise or blue, which are at lower elevation. So we have a higher elevation, lower elevation difference that we can see in terms of just looking at the colors. But further, we can see some interesting patterns. We can see some interesting landforms already just by looking at what we see here. And this is called a topographic map. It's essentially showing the undulation, the elevation, the ruggedness of Indiana. And of course, you can see a general pattern. The northern part of the state, it's pretty darn flat. In the southern part of the state, you have a lot of changes, a lot of greens and greens and browns and whites and yellows and all of that. So it's a lot more ruggedness, lots more change in topography in the southern part of the state. One thing I noted here was put in the rivers. You have a situation, these two lakes. What do you think's going on here? These are two lakes, kind of looking at side by side. What do you think these two lakes? What's that? Oh, sorry, my fault. Yeah.
Rivers that maybe like dried up and left behind a little lake.
You're on the right track.
Well, one, if not both, I think are man-made.
Boom. Exactly. So rivers went right through here. Essentially what they did was they dammed it. They just put a dam up. So essentially what these are lakes, but they're not natural lakes. They're man-made lakes. Lakes in which what we do is we essentially put a dam, put a big wall, and over time that river then backs up, creating a big old lake. And you can kind of see that here when we look at this feature right there. You can see right through there how the river used to go right through here. But over time what they did was they just dammed it. So they dammed it up. So then we have a lot of those in the southern part of the state, a lot of dammed up rivers. So that's one of the things is we have very few natural lakes in Indiana. If we do have a natural lake that wasn't made because someone put a dam up to block a river to make it look big, then you'd find them in the extreme northern part of the state, and that's the last thing we'll talk about today, and those are called Caddo Lakes. So all those are dammed up rivers. Whoa. So here we have Indiana, in which once again we have a continental divide going right through us. It's one of my passions, one of my goals in life, is to get these to be shown as markers actually on roads. So you know that when you're up in the northern part of the state, when you're driving on, for example, I-65 North, all of a sudden I want a sign that says, you are now in the Atlantic Ocean Continental Divide, which separates the Gulf of Mexico drainage basin. So that's one of my goals to do before I pass on. Anyway, so here we have all these rivers essentially flow into the Gulf of Mexico. And so if I went out to the street level and I urinated on the street, eventually that urine will make its way to the Gulf of Mexico. So everything drains, in our case of Indiana, everything except the extreme northern just tenth of the state drains towards Evansville, towards the south and western parts of the state. So we have all these various rivers here that all are working their way towards the lowest point in the state. We've got two rivers right through here. Two rivers that couldn't be farther from being any. Let me say this again. These are two rivers that have absolutely nothing in common other than they both have the same name. So these are both of them are the White River. The one is the West Fork, and the other one is the East Fork. Why do you think they named him that? Who do you think named him that? What was maybe the perspective? You think? It was Native Americans, but it was actually the French who were the ones that named it. It was, I'm going to be butchering my French, Le Blanc, Roux. Yeah, sure, maybe, I don't know. So the French, essentially the French came up the White River, and they came up the White River, and when they said, okay, well, there's the West Fork, and there's the East Fork. These rivers are completely different. They shouldn't really be called the same thing at all. but it all dates back to way back when our early French explorers settled Indiana. They were using the rivers, using the rivers overwhelmingly to travel, and came up this way and saw the West Fork and saw the East Fork, and the names have stuck ever since. We look at the West Fork. The West Fork of the White River, this is where it starts. It's its origin. Its origin is in some guy's farm field just north of Richmond, in the area around Winchester. Those of you who might be from that area. And so it starts in some guy's field. Whereas the East Fork starts at the confluence of three different rivers. Three different rivers all pretty much come together in my favorite city, Columbus. They all come together there in Columbus. And so here we have two rivers that are absolutely different. One that starts in some guy's field, another one that starts as three rivers come together here to form the East Fork. Further, other differences, one goes through major cities. The West Fork goes through Muncie, Anderson, Indianapolis, whereas the other one pretty much just goes through Columbus and scoots through rural south central Indiana. Let's just do a mini pop quiz. So here is something, maybe this will help you with your fluvial landforms, your river-created landforms. But by looking at this, I want you to be able to identify where each of these 5 things that are blinking are found. I might have to dim the light so we can see this better. Anybody know Teddy Pendergrass? Okay, there we go. Thanks, Teddy. All right, let's see if we can see these things. Does anybody see the floodplain? I do. It's pretty much the whole entire picture. The whole entire picture is the floodplain. And you can see it's quite flat. This area is quite flat. I know it's not the best perspective, but you can see it's quite flat. So what happens is over time, this river has just been changing course. It's been going back and forth. So as it goes back and forth, it essentially smooths out that area. And so it creates a floodplain. So we can see throughout most of this image here, that is the floodplain, which once again is created by a river changing its course over time, and thus the word plain, P-L-A-I-N, flat. Anytime you hear the word plain, think flat. Where might we find an undercut bank?
C1. That bottom shape here for the.
Tell me where to go. Oh, you can't see it. Great. We can't see it. Where did you go? No, you don't see me?
Maybe like where the as you come down the dotted line, the first little U right there, would that be it?
If you
Do
go.
they have a laser pointer? This would be You can't see my mouse? You can't see it? No?
We did at one point. I don't know how.
Yeah, why would we have one point work? No. We see now?
Yeah.
Oh, jeez. I'm tired. All right.
It'd be the riverbank that's towards the most bottom right corner where the
Southeast.
We'll see what we can do here. Solution to every problem. So you're saying right about in this area?
no,
The
you go to the right,
Yeah.
you're right.
My right?
Yeah.
Yeah, you go on
That's
on your right.
Man, why would
You can kind of see that U shape where there's trees on one side and the bare ground on the other.
So if you look at
The
the
undercutting of the bare ground side.
like in the
Point
middle
bar
of
would be
the lower things, probably the
Oh, here we go. Here we go. Oh,
Wow.
oh yeah, all right.
Wow.
Round of applause for everyone. Finally. Thank you. Finally. All right. So yeah, tell me where to go.
Keep going over.
Yeah, and that
Keep going. Keep going. There's your undercut right there.
There's the cut bank.
Opposite of that is the point bar.
Boom, exactly. And so what we got is the cut bank, or the undercut bank. The undercut bank's always going to be on the outside of the meander. So it's going to be quite steep, or the slope is going to be quite severe. So just think of it as you're going down the slope here from here down to the water. It's going to be rather quick descent. Whereas on the other side, the inside of this meander, you have that point bar. And so it's also called a point bar deposit because over time sediment collects. And that sediment has collected right through here in this particular area we can see right there. So that's over time sediment that's collected. It's even clearer to see when we go over here. You can actually see the sediment form and develop and deposit, all that collect on the inside of the meander. So we can see how the outsides have what we call a cut bank, a very steep slope, whereas on the inside we have of the meander we have that point bar deposit that starts to collect here. So we can say that there's a point bar deposit there, and then the undercut bank on that outside. So undercut bank also right there. Last two, a meander scar and oxbow lake. So someone for the top 3 rows. Where can I find a meander scar or an oxbow lake?
Meander scar
No, you're fine.
Sorry.
You're fine. No, that's good. So you're talking about right here?
Yeah.
Yeah, so that's looks like a meander scar. I don't see water in there, so that's definitely a meander scar. So we see one there. We can kind of see one here. We can see one there. That looks like another That looks like a meander scar there. And then this looks like an oxbow lake. I do see a little bit of water there. So these oxbow lakes. So every oxbow lake will eventually dry up. Every oxbow lake, just like every young child eventually becomes an adult, every oxbow lake eventually becomes a meander scar. Why?
What about the bottom right?
There's nothing feeding.
There's no more water feeding it. Where beforehand, flowing water from somewhere upslope was feeding that particular area. But now it's cut off. It's its own little thing. Over time, evaporation will then cause the water to be removed, and it'll become a meander scar. What were you saying,
What
Don?
about in the bottom right?
Bottom right?
Is that water?
That looks like it's just part of the floodplain area. So that could be water, could be standing water. So a lot of what you find in the floodplain is whenever you do get a big rain event, you'll get a lot of flooding. So it's not widespread flooding, but you get a lot of flooding, especially the closer you are to the river, which is essentially the water table exposed. So these areas, whenever we have big rainstorms, these are always going to be flooding. And it's especially these flat areas, that makes sense, because flat areas are more likely to flood than rugged areas, because that water just goes straight downhill. Where in these plain areas, it just kind of sits there and waits for another river or waterway to take it out of there, or for nature just to evaporate it. And then we have the water cycle and work.
This might be a silly question, but how do you know based on the river when it's meandering? Is it because it's right there, it's a really huge U-shape and it kind of goes away?
Yeah. So you can say whenever the meander, the bigger the meander, the more point bar deposit and undercut bank erosion and deposition you would find. Here, if you see this meander here, it's kind of a meander, but you see a little bit of a cut bank on this outside of this meander, and a little bit of a deposit, a little bit of a growth here on the inside. But you look at the ones in which that are really big meanders, like this one here, or this one there, that's when you really notice the point bar deposit collecting in a large amount, and then the undercut bank much more severe than it is maybe through there. Yeah.
What is the yellow line and blue line?
Yellow line is the White River West Fork. Actually, good thing. I'm going to go back here. The yellow line is the White River East Fork, and the blue line is the Muscatatuck. So this is where two rivers come together here. So I forgot to mention that. So that's just me zooming into this specific area where these rivers come together. Cool. All right. Now let's talk about our glacial history. So now this is going to be pertinent to the notes that you have in front of you. So if you don't have them, raise your hand so I can make sure you get them. So Indiana's glacial history. So we look at us in the video lecture. I believe it's live this week. You're learning about mountain glaciers. So mountain glaciers are cool and all. In fact, they're really cool. But they have nothing to do with Indiana. They don't do anything to explain why Indiana looks the way it does. So I just kind of showcase some things as far as rivers, how and why Indiana looks the way it does, as far as different elevation, continental divide, and all of that. but you look at the number one, the biggest influencer in explaining why Indiana looks the way it does is the role of glaciers. In particular, big old continental glacier. And so today what we're going to do, this is stuff that is already, once again, it's included in the lecture notes. What we're going to do is we're going to explain and introduce the idea of a continental glacier, what it is, but then also look at the landforms that it created. And all of these different landforms we see somewhere in Indiana. We see them somewhere. And so each of these 5. So for a future question, if it ever is asked for you to describe resulting landforms from Indiana's glacial period, make sure you speak to a lot of these different characteristics, whether it be explaining continental landforms, continental glaciers, some key characteristics of them, but then also being able to explain each of these different formations and kind of be able to explain how they formed, but also where we might find them, which also relates to the map there, the right-hand side of the map, I believe, which is what we're going to do today. We're going to try to understand all of these various chicken scratches that we see on this particular state drawing or state topographic map. First off, continental glaciers. So we go through the lecture notes, but first off, we have to distinguish these suckers from alpine glaciers. Mountain glaciers, they're big. They're very, very powerful as far as erodiers. But they ain't nothing compared to continental glaciers, which are massive, enormous features. So these are, of course, as the name implies, continental glacier. They're going to take up, at times, an entire continent, or a huge amount of land area. So these are massive land features in terms of their size, but also in terms of their weight. So this is kind of hard to imagine, but just imagine, just go outside right now, go look at the surface, and just imagine about a mile up in the air. That's about how tall these continental glaciers were. Think about that. About a mile-high sheet of ice, that's the entire continent, or much of the entire Great Plains and Midwest, as far as its size, much of Canada. These suckers were massive. So of course, they're going to have a large amount of erosive power. In fact, they're nature's bulldozer, I believe is maybe what it says here somewhere. So the enormous features. So big that they actually cause the land to almost sink. They put so much pressure on the actual surface that it actually, in parts, has actually poked down into the asthenosphere below. And so what's happening now, in particular in Michigan, it's something called isostatic rebound. I don't know if I mentioned this in video lectures, but essentially what's happening is, because that weight of the glaciers is no longer there, the surface is slowly coming back up. It's coming back up because that weight has been removed. So just imagine something that was heavy, pressing down on something, and then it's released, it's going to then rebound and retake its shape. And so actually what's happening now is Michigan, it's not something you're going to notice, is actually slowly springing back up as that weight of that overlying glacier is no longer. So other things to say about these suckers. Is we still see it today. So the same glacier that was over Indiana, right where we are right now. You go back about 14,000 years ago, we would have been underneath a big old ice sheet. That same ice sheet's still around. It still exists. He or she hasn't gone anywhere. They're just now up there in Greenland. So we look at Greenland, that big white sheet in Greenland. That's the same ice sheet, same continental glacier that came down, moved down into this area right here, and then since has retreated and headed back up to Greenland. So when we look at Greenland, that ice sheet today is essentially what was once a continental glacier that spanned the entire continent. So ice sheets, we still see these two notable areas, and of course it's so easy to find them on a map. Look for the white areas. So there we have a white area down there and a white area up there at the top, Greenland. Those are our two continental glaciers, our two main ice sheets.
This is probably going to sound stupid.
No.
But so do people just like live on ice then?
No. So there are very, very few people that live in Greenland. So if you look at Greenland, it's that big ice sheet on this, well, it's on both of them, but it's more up the upper right-hand corner. You can kind of see how the sides of it have areas that aren't ice. Those are where people live. So they live very much right on the coastline. They live right there where glacier meets the sea. But they're extremely limiting as far as where people can live. So Eskimos, those are kind of, the popular culture, kind of the people that live there, but very, very, very few and far between. Very difficult to live on. More because there's nothing to eat on. There's no plants, and because of that, there's no animals. And so kind of that vicious cycle.
Are those glaciers affecting the temperature anyway? Or
Well, that's a way over my head. But there's no doubt that there's, the glaciers, the fact that they're white helps to promote cooling. And so if the glaciers are shrinking, that's only going to add to the heating because there's less white stuff. Water is now going from ice to water. And so that's what's kind of adding to even more the urgency to, I would say, lessen, I'm not going to go there, but just to lower the warming of the earth. I'm not going to go into the climate change discussion right now, but there's no doubt that helps promote cooling, and fewer of it, less of it, is only going to increase temperatures, one would assume. But nature, we're still learning about it. All right, so here we are 3 million years ago. Anything you notice as far as what's absent from this map? The Great Lakes. Our good friend of Lake Michigan, Huron, Superior, Erie, and Ontario. They ain't there. Why? Because they haven't been formed yet. So this is all before a continental glacier came down and moved from the ice sheet there in Greenland, way up here, moved down and actually came and covered this particular area. And so more recently, about 125,000 years ago, we now have the glacier arriving and covering this particular area. And so these glaciers are big features. Like I mentioned beforehand, huge. So we're just going to kind of use an illustration of this. And so where did my skill go? Put it inside the box. Did I put it inside the box? I'm so organized, aren't I? Yeah, there I am. All right. So let's just go ahead and kind of make a visual. So future teachers, if you ever have to teach, how do you open this? Here. If you ever have to teach this stuff, here's how you do it. First off, you go ahead and open up the bag before you start class. I always suggest double bagging it. You always have bowls. So we'll go ahead and we'll just put in our debris. We'll just use this as different sediment, rocks. So just imagine anything in nature's way, or sorry, anything in these glaciers' way. Once again, what do I refer to these as? Nature's bulldozers. Did I say that earlier? Well, if I didn't say that earlier, I'm saying it again. So nature, not nations, bulldozer. Go ahead and throw our glacial raft in there. And so pulverizing. This is a huge amount of weight. A mile-thick sheet of ice, the entire continent. We're talking a huge amount of weight. And so what that's going to do is it's just going to pulverize everything in its path. Just imagine that. A mile-thick sheet of ice, trees, women, children, whatever is in its path, it's just going to crunch up and turn to dust. And so how does that happen? What we have now is we have the glacier that pulverizes and destroys everything. But it moves. It actually moves and it advances and it retreats. And as it does that, it creates landforms. How does it advance? So it's not like, we have this image of advancing and retreating like a military, like an army. Here we go, we're all advancing, and now we're all retreating. It kind of works that way, but it kind of doesn't. How does it advance? If we can think about a big glob, let's think about pizza instead of chips right now. Let's think about a big dough of pizza, big thing of pizza dough. If I put weight on the top of it, what's going to happen to the pizza dough? Is it going to expand? It's going to expand in different directions. And so what happens is more weight, more snow, adding to the top, adding further upslope, or further at a higher altitude, higher latitude, is going to add weight, which is going to actually push the continental glacier. It's going to push it down, causing it to move. So that's how glaciers advance. It's actually the weight of the snow that over time accumulates, gets so heavy that it actually then starts to push and move this continental glacier forward. And so we have these two things, the zone of accumulation and zone of ablation, which, do I mention in the video lectures for mountain glaciers?
Yeah.
Yes, so it's the same idea here. So we have the area where we have more accumulation, we have an area where we have more snow being added, more weight being added, but then towards the front of the glacier we have more destruction occurring, more deposition and erosion and all of that just plowing and obliterating everything in its path. I didn't say in the lecture notes. Not that far. Let me see if that's. Yeah, they're really slow. I'm trying to find. See if it's in my notes. I used to teach it. It was something like 5 feet a year or something. Something really, really small. I'll give you all a bonus point if you can find that answer. So someone can find the answer. How fast do glaciers move? And I'm sure you can find that answer before we're done. How fast do glaciers move? So look at continental glaciers. I know I had that somewhere, but I guess I don't teach it anymore. It's really, really small. Really, really, really small amount. That's probably not a good tool to tell everyone to go do something right before I do a demonstration. 5 meters a year. Oh, so now I gotta come up with the point. All right. Smile. So if you're in this photo, you'll get a point. Oh, my battery's already done. Come on. You know, it's actually illegal to take photos of students in class. Isn't that weird?
Why is that?
I don't know. I mean, I guess it's legal for me to publish. That's why I can't take pictures of sleeping people. I gotta make selfies instead.
I didn't get to see those. It didn't show up. Those selfies that you took. I was disappointed.
Okay. Maybe in the future I'll send them to you. They're on my Facebook page. Anyway. All right. Where was I? All right. So we were talking about the glacier. So the glacier that came through, went through this area, like I said, massive. So massive, we're going to see it, its actual size and its width right here. So you can kind of see the extent of the most recent glacier. It's essentially all these glaciers that have over time come through this area. They pretty much have all never gone farther than there. And what do you know? At the edges of where it went, what do we find there? Rivers. Our good friend, the Ohio River, and our other good friend, the Missouri River, both formed at the edge or the boundary of this continental glacier. So that's essentially the origins of them date back to this most recent glacier. If we go back way back when, remember we looked at this image? We don't see them. The Missouri River, the Ohio, they're not there, but they are today. It's all because that's where the glacier stopped. The glacier stopped and created those various features. But once again, no, not once again yet. Anyway, so here is a geologist, a real person, who actually identified the most recent glacial boundary. And that's called the Wisconsin Glacial Boundary. Now, the names of them are kind of weird, but just the most recent is called the Wisconsin. We have an older one called the Illinois. Don't really worry about how and why they named them, how they did. Just the most recent is the Wisconsin, and we can see its glacial boundary here. And so going on that map, on the left-hand side, you can go ahead and maybe draw it, or you can also see it on the right-hand side. Right there, we have the glacial boundary of the most recent glacier, the Wisconsin Glacier Boundary. It stopped right about there. So it stopped all the way from about Terre Haute to about Columbus over to Richmond. It's where we found this glacier stopping that I just showed beforehand. And when we think about these glaciers, when they advance, that slow accumulation of snow, that 5 meters per year, is that what he said? 0.5 meters per year, even worse, or even slower. 0.5 meters per year, that slow march. What happens is it kind of comes in lobes. And so what happens is this moraine, this most recent glacier, it wasn't like it was just one big glacier that came in. It was these individual lobes that come together to form one entire glacier. You can go ahead and show that again. So we have these different lobes of these continental glaciers coming by, and trust me, when they're moving, they are pulverizing, they're flattening everything in its path. So one of the things, if you look at northern Indiana, before the glaciers looked just like southern Indiana. So you go down to Seymour, go down to Bloomington, go down to all those areas in south central Indiana. You see how rugged it is. Go down, don't do it, but if you really have to, go to Kentucky. and you'll see exactly what it would look like in northern Indiana before the glaciers. Northern Indiana looks just like that. Today, it's extremely flat. In fact, it's super flat, northern Indiana. Why? The glaciers came through, flattened everything in its path, and then eventually stopped there. But why is south central Indiana not, why is it so rugged and it's not flat? Because the glacier didn't come through there. The glacier didn't come through and flatten it out. And so this gets us to our term, an end moraine. So an end moraine, unsorted deposition, gravel especially, at the end of a glacier. So an end moraine, we're going to see a particular pattern at the glacial boundary, where the glacier stops. We're going to see very rugged topography. We're going to see rugged terrain. You're going to see a particular predictable landform. It's going to be very linear in shape, in the sense it's going to follow that boundary as well. So from about Crawfordsville to Nashville to Columbus to Shelbyville over to Knightstown. For those of you who know your Hoosier geography, in and out, kind of this line right through the kind of the south central part of Indiana. Also, though, this is crucial to understanding how Long Island formed. So Long Island is that island just off of New York City, just off the coast of the Atlantic there. It actually formed because it is an end moraine. So the same glacier that stopped in south central Indiana, essentially stopped in Nashville, Indiana, for example, it also stopped in New York. And it stopped there and created the Long Island of New York. So I'm going to try to showcase how that happens. So we have the glacier, this whole end moraine, how it happens. So extra weight being added is going to cause that glacier to move. And eventually what it's going to do, it's going to act like a conveyor belt. So not only is it a bulldozer, which is pushing everything in its path, the bottom of the Continental Glacier also acts as a conveyor belt. It's essentially bringing stuff, bringing sediment, bringing gravel, bringing rock, bringing sand, silt, whatever, bringing it to the front. So that also adds to the fact that the bulldozer effect, but also the conveyor belt effect, it's going to create a rugged feature. And it's going to create a rugged feature, like I said, at the end of the glacier. It's going to essentially pulverize and push everything to a certain spot. And then when it stops there, it's going to create a physical feature. Anyway, that just bothers me that triangle should be in the front of the glacier. But anyway, who cares? All right. So what happens is the glacier then, it recedes, it advances, it retreats. And it's not like a deal where it turns back and heads the other direction. All that happens, it gets warmer out and it just starts to melt. That's all that happens. And so it's not like it just kind of turns back and goes the other direction. It just starts to melt as warming temperatures occur, and that causes these suckers to then retreat. So like I said, we pulverize, we destroy, we essentially, everything in its path. Glacial erratics, granite from Canada, trees from Michigan, sediment from northern Indiana, all of that is essentially pulverized and carried and then eventually dumped. But now we got to make some land features. And don't worry, we have janitors who will clean this up. And so here I am, my Big Bad Glacier, pulverized, huge amount of weight. And so essentially what happens is the glacier advances. It advances, then it stops, and it starts to retreat. And look what it advances, and it retreats. And look what we just formed. We just formed an end moraine. It's essentially a Continental Glacier advancing everything in its path, even our glacial erratic, even our skittles, everything in its path is essentially pushed to the front. And so essentially what we've done is we've created a rugged topography. And so this is a land feature that you can see all throughout south central Indiana. For example, on your way to Bloomington, if you ride on 37 on your way to Bloomington, you go on 37, you go up, and then you look at the beautiful city of Martinsville. It's kind of down below you. You can kind of see that. When you're on 37, you look down, you can kind of see Martinsville. That's the moraine. That's the end moraine right there. If you go to the Outlet Mall in Edinburgh, and so you have the Outlet Mall in Edinburgh, you keep on going past that exit on 65 South. Keep on going past, you're going to go up, and you're going to go over. That's the end moraine. Go down to Nashville. Why is Nashville so hilly? Why is it so rugged? It's because it's at the end moraine. It's actually where two end moraines have stopped. Two other glaciers, let me say, have stopped. And so it's got two different glaciers that created that same rugged topography. And so that's our first feature, our end moraine, which is very linear, and we've kind of, I hope, tried to understand how it forms. Now let's go to our next one. All right, so Long Island, once again, Long Island. Here's its particular shape, the blinking up. So Long Island all the way up to Cape Cod. Essentially, we're formed from the same feature. So that same feature. So we have a glacier, same glacier that came through and stopped in Indiana, stopped here in Long Island. And so essentially, as it retreats, it then essentially all that water goes downhill. And so it's essentially creating an island. So here is Long Island. So here we have Long Island Sound, JFK Jr. somewhere in there. Bad joke, Andy. So over here is the Atlantic Ocean. So here's Connecticut. So essentially, Long Island is just like this, an end moraine, in which over time the water is kind of filled in the gaps on both sides, creating an island when all it is just an end moraine. Further, we have another type of moraine, the next one, and that's a recessional moraine. A recessional moraine, I don't know if I'll ask this, but if I ever do, you know the answer. A recessional moraine, it's always behind the end moraine. Or in other words, in this case, the recessional moraine is always going to be on this side. It's never going to be in front of an end moraine. And that makes sense. A recessional moraine, as the name implies, I'm not the one that came up with the name, but recessional, kind of, it's receding. So it's receding, it's heading backwards. And so I'll just go ahead and I'll do my demonstration here again. This is kind of fun. So here we have a glacier that's retreating, but we might have just a few thousand years of cooling. So a few thousand years of cooling, this is going to cause that to go back to 0.5 meters per year or whatever, and it's going to create another moraine, and it's going to head back and create another moraine, and it's going to head back, and so we have these periods of cooling and heating and cooling and heating, and so as it retreats, it creates these parallel moraines that are behind that end moraine. These parallel moraines that then form behind the end moraine are the recessional moraines. So essentially, like I said, periods of standstills. And so the glacier advances, but then it's not really for long. It's just for a few thousand years, and then it retreats, and then it advances again, and then it retreats, and it creates these parallel almost to each other moraines as those lobes of these glaciers start to retreat and head backwards. So another way to visualize this, I just created my end moraine, and so now I'm going forward again, I guess. I'm going to create another feature. What are we looking at? So here we have an advancing glacier. It's going to create another moraine, and then it's going to then retreat, so it's creating these parallel ridges. So here we can find these in Indiana. So I take out our lobes. What do you notice first off is a lot of blue added. Why is a lot of blue added to the map?
Melted water.
Melted water. Think about that. Entire state of Indiana wide, mile thick. That water's got to go somewhere. So that water is absolutely critical to understanding why those rivers are located where they are, but also what they did is they did a lot of eroding, massive amount of eroding, as all that water has to go somewhere, and so it cut through. And created all these river valleys that we see, especially throughout southern Indiana. So where do we see recessional moraines? We first off see one just south of Lake Michigan. Anybody from the region? And so you'll notice this. Valparaiso is a little bit higher elevation. Especially when you get on 65, it's a little hard to see. But just south of Lake Michigan, closer to Valparaiso, you'll see it's very rugged. You actually go up in topography, and all that is a recessional moraine. All it is just a kind of a period in which the glacier advanced a little bit and created this certain ridge right through there. The more obvious ones, the more noticeable ones, are the ones over here by Fort Wayne. And so you can actually see these on this particular map, I hope. So these are all recessional moraines. I don't know if can you see them on the topography deal? Yeah. Did I just zoom in? Wow. That's cool. Yeah. So you can kind of see them there. So those are examples of recessional moraines. And so as you go north on 69, This is stuff that, some people that are really geeked out about this will do. But I did this. As I was going up to Fort Wayne, I thought, well, if I'm going to go to Fort Wayne, I might as well enjoy myself. And so what I did was I actually tracked, I wish I had it with me, but my GPS, it tracked and it located each of those recessional moraines as I was going north on the highway. I kind of recognized, oops, we're going up, now we're going back down. So it recognized that as you go north from Indy to Fort Wayne, you go over these recessional moraines, which might appear to be just little hills, but they're actually created from these stops and stands from a glacier retreating. What might this feature be? I'll give you a hint. It's an aeolian feature. So it's not something I've covered today, but I've covered before. Aeolian processes, wind processes. What's that? Yep. What are they called? Well. What's that? Lurch. This is kind of a weird, I believe, German term. It's actually like Lurch. There's no R in it, but those are those Luss deposits. Those Luss deposits essentially pulverized sediment that is pulverized so much, pulverized to a powder, to being super, super small, that actually wind can actually move it around. So what we have is we have those aeolian, or those Luss deposits that are found in a particular part of the state. So it's particularly there on the eastern side of the Wabash River, on the eastern side of the West Fork of the White River. Why is it on the eastern side, not the western side? What's that?
Because the land comes westerly.
Ding, 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 ding. And so that's definitely correct. And so why is it that we see on the eastern side of these rivers all that deposit, all that settlement collect? Because the patterns in this particular area of the country take things from west to east. So those are the westerlies in action. So we don't see this deposit collecting on the western side. It's essentially it's been blown over to the eastern side and over time it's collecting. So this is critical. Certain soil, certain agricultural crops really like this type of soil. They like the soil with a lot of loess. So that's why this particular area has some good farming, even though it's in the southern part of the state. Most people think of the northern part of the state. Of course, we have a sand dune up here along Lake Michigan. Sand dune is something I also described in the aeolian features discussion. All right, so here we have 125,000 years ago. Now we're going to remove those glaciers, and now what do we see? So I'm going to go back and forth. Tell me what you see. So back in time, 125,000 years ago today. What are some patterns that you notice, some things that you notice? I'll start us off. There's less amount of white stuff. Okay, you're next. More lakes. A whole lot more lakes. Where are those lakes found? Overwhelmingly where the glacier was. Overwhelmingly exactly right here is where the glacier was. And so as the glacier retreats, we can see a ton of these lakes. We don't see a lot of lakes there south of the glacial boundary. So we can see that. Other things we note.
Receding coastline.
Receding coastlines. So we have receding coastlines. Go look at Florida. You can zoom in. Yeah, we can't zoom in and go back and forth, I don't think. So if you look at Florida, if you can really focus in right there, you can see how it's bigger yesterday than it is today. And so this is a huge problem, and this is something that it's been in the 125,000 years in the making for Florida, is they're soon going to be underwater. So all those carnivorous meth have got to find somewhere else to go, because eventually they're going to be underwater. So you add that to the fact that they're developing a lot of marshlands, so they're taking away nature's sponge, only adding to the problem of advancing, of rising sea levels and essentially the coastline getting smaller and smaller and smaller. That's for the most part what we notice in this particular advance. So this is looking at Lake Michigan. So I found this on Google, but I thought I'd share this. But this you can kind of see this glacier, Lake Michigan, how it formed. Lake Michigan is actually a lobe of this glacier. So it's a lobe of this glacier that's created, scoured. It created this huge bowl, this huge valley as it scoured the landscape. Then it melted and then filled that bowl.
Does any of this have to do with Atlantis? The city of Atlantis?
Where I've heard that before.
It's
Where is
like-
Atlantis?
I think it's in the Atlantic someplace. I guess it was an actual city that flooded.
Yeah,
Before
I don't know. I've heard that before.
Yeah.
But there's a ton of cities out there that have been flooded. Some of them for man-made reasons. In fact, I'll take you somewhere else later in the semester. The Three Gorges Dam, a man-made, obviously waterway, water feature. That essentially, because it was so big, it actually flooded 13 cities the size of Fort Wayne. Did you imagine that? 13 cities that are now underwater. 13 cities the size of Fort Wayne, but you got to move all those people. You got all those dead bodies and cemeteries and all that, and it's just amazing. So that was, it's the world's largest hydroelectric project, but that's not uncommon for buried places. In fact, there's an area over Geist, there's an underwater village where the Geist Reservoir is. It's something I haven't looked up even further, maybe some of you know that, but there's actually an old village that when they made Geist River, or Geist Reservoir, the big old lake, for the wealthy there, essentially it flooded that town. But anyway, that happens a lot. But since 14,000 years ago, I don't know if there were humans in this particular area. If there was, their concerns weren't so much about being flooded; they were more about woolly mammoths, probably. Yeah.
I'm from Anderson,
Cool.
and right now they're actually working on a project where they're going to Scatterfield is like a big street for us. And I guess there used to be, the White River used to run through there, but they kind of sort of blocked it off because whenever it floods, whenever it rains, it really floods in that area. And so they're going to open it back up and re-flood that part of our city.
And so what's happened in Anderson, as you know quite well, is it's seen better days. And so it's lost of jobs, lost of people. So what's happened is a lot of manufacturing's gone somewhere else. So Anderson has a problem. They have this crisis. How do we keep people here? And so one solution they've come up with is creating a recreational area, creating a lake, creating an area that's going to attract maybe lake homes, people to come do water skiing and boating and all those things. They kind of offset the losses from manufacturing jobs going elsewhere. That's a very, very interesting thing. I'm definitely interested in that. I heard that about a year ago, but that makes sense. And it's their mayor or their leadership that's thinking outside the box. Because there's definitely a problem. And when I graduated high school from Center Grove in 1998, there were 3 high schools in Anderson. Now there's just one. It kind of showcases the out-migration. Further, when you drive up through Anderson, you can see big old, huge roads, but hardly anybody driving. It's almost like a ghost town. But it'll be back. It's so close to Hamilton County, it's going to take advantage of that going forward. Anyway, getting short on time, so I'm going to cruise through this remaining stuff. And so here is a photo I took from the sand dunes just off of Lake Michigan. So here in Indiana, we do have a beach. We actually have a cool beach, but it's really, really hot. The sand gets really, really hot in the summertime. Don't walk barefoot along the dune sand. Anyway, till plain. What is a till plain? Till plain is always formed behind the end moraine, and it's an unsorted mix of silt, clay, sand, gravel, and it's deposits that when the glacier retreats, it leaves behind. And so throughout northern Indiana, it's very, very flat. You're going to see rolling hills. But essentially, when we think about these glaciers, when they retreat, they just pretty much just drop everything. They just drop everything in its spot. Whereas things above, things away from the end moraine, further away from the end of that glacier boundary, essentially the sediment gets more sorted. Essentially, rivers carry that sediment, start sorting into those layers that I've talked about in a previous video lecture. Whereas in the places behind the end moraine, everything just is dropped and plopped, and just plopped right there in places. So this is going to be found in abundance in northern and central Indiana, this till plain. In fact, it's going to take up much of the area. Combine all of these factors, flat areas with rolling terrain, a variety of sediment that's just kind of plopped in place, is why we have the best soil in much of the entire world right in this particular area, the Tipton till plain. Agriculture, it likes things to grow. It likes very smooth surfaces because it's going to hold the water. If it's in steep slopes, that water is going to flow straight downhill, and it's not going to collect, and those little roots can't get their water that they need. So flat areas are extremely good for agriculture, and of course, in the northern part of the state, we're going to see that. And so all this particular area here represents the Tipton till plain. So like I said, much of northern Indiana is comprised within this particular region right through there. So all this is called the Tipton-Till Plain. It's called the Tipton-Till Plain because right in the middle of it's Tipton County, which of all the counties is the flattest county in the state of Indiana. So that's why it's called the Tipton-Till Plain. So damn good agriculture right there. So if we all know this, but we know why now Indiana, the northern part of the state, is so flat, and the southern part of the state is so hilly. So Indiana has a very, very different landscape as you go from north to south. So while people all outside the state think, not first off, they think we're all bigots, but they also think that we live in a state that's completely flat, nothing but corn, and that's definitely not the case. So we definitely see here we're quite flat. Here we have a granite rock. We find these throughout a lot of subdivisions. A lot of subdivisions, as they build homes, they'll come across these big rocks, and eventually what happens is someone who doesn't want people driving through their yard, driving their car through their front yard, they put these big, huge boulders to prevent that. But these big, huge boulders, these big, huge chunks of granite are found nowhere in Indiana. You can go down, you got to go through, layers of soil, layers of limestone, layers of this, that, and the other. Then you finally get to the granite in Indiana. So how in the hell this big, huge chunk of granite, this rock, that's not from anywhere from around here, how does it end up here?
Got push.
What's that?
It's our skill.
It's our skittle. So this is a glacial erratic. Oh, I guess we got orange M&Ms. So whatever, your skittle's lost. So what we have is we have these glacial erratics, these big, huge chunks of rock that were plucked away way back up in Canada, brought with them, and then just essentially dropped. The glacier just drops them. And then drops them in spots. And so throughout much of northern Indiana, farmers' fields, they have to negotiate these suckers, these things all the time. And then, like I said, in subdivisions all throughout metropolitan Indianapolis, you see these glacial erratics being used in people's front yards and all kinds of things. So we have this particular area here that I got a question mark on. This area right through here looks a lot like areas on the other side of that red line, areas north of the glacial boundary. So what might happen there? What might have formed that?
Is it possible part of the glacier broke off?
No, the previous glacier didn't go any farther than right there.
Erosion?
What's up?
Erosion?
Erosion?
Like the leftover from the glacier.
It's actually from the previous glacier. So you have to think about these glaciers. When one comes through, another one might come over it. When one comes over it, essentially removes the evidence of the previous one. Then you have another one come over, another one. So the most recent is the most recent come through here. And so all it is an older glacier that made it even farther down. And that older glacier made it even farther down and made it right through here. And so essentially what it did was this is the Illinoisan glacial boundary. And so this is just till, just the same stuff that's formed up here from this glacial boundary that was formed from a previous glacier. So all that right there is just essentially till area from a previous glacier, one that came before this particular area here. And so this remains this one little area of Indiana that's resisted glaciers. That's resisted glaciers coming over. And so because of that, all that sediment hasn't buried and came on top of the underlying bedrock. And so you have bedrock very close to the surface. In this particular area, what's that bedrock? It's found in abundance in this particular area of the state, South Central. Limestone. And so limestone is very, very close to the surface. Combined with the fact you get rain, that's why there's a lot of sinkholes and karsts and caves and all that through this particular area, is because glaciers never affected it, and thus the limestone is at a it's closer to the surface. That limestone, it's all over northern Indiana. It's just buried under all the sediment that's been left behind by the Continental Glacier. So here you can see the sinkholes, kind of, it looks like a golf ball dimple, all north, just north of Indiana's first capital in Corydon. All right, Outwash Plain. So I'm just going to get through Outwash Plain quite quickly. So Outwash Plain. Outwash Plain is going to be, for the most part, on the other side of the moraine. And so once again, it's going to be on this side, for the most part, the Outwash Plain. And so we have this huge chunk of ice that melts, and so all that water is going to then go, of course, downslope, in the case of Indiana, go towards Evansville. And so these rivers then take with it certain sediments. And typically it's the lighter sediments. Of course, water is not going to move big, heavy stuff. not to move big heavy boulders. And so typically, that's why the in-moraine also has even more gravel, is the sands, the silts, the smaller stuff has essentially been removed by the flowing water. So the flowing water then carries that sediment somewhere else, and we have this general pattern here, in which the heavy stuff stays up closer to the rugged areas, the in-moraine, but the lighter stuff can be carried farther. So this all gets to the whole bed load, suspended load, and dissolved load from a previous video lecture. So all that stuff kind of builds and builds and builds to help to understand why we have layering in the outwash, where in the glacial till we don't. Glacial till, keep in mind, everything just drops in spots, is very erratic. Whereas in the outwash plain, you have these particular layers in which the heavy stuff on the bottom and the light stuff on the top. So knowing that, which one of these is glacial till and which one of these is outwash? Glacial till is on the left. You can see on the right. See a little bit of, you see layering. So that layering is all about rivers carrying sediment. It can only carry lighter sediment, smaller sediment. It can't carry boulders. And that's why we see the glacial till, the glacier essentially dumped everything in spot, and that's why we have very erratic, not really, it's unsorted, all kinds of stuff. We don't see the layering that we would see in the outwash on the right-hand side. Both of these images are from Indiana. So one's up in the northern part, the other one's in the southern part. The last and final feature we talk about today is the Caddo Lake. So Caddo Lake, essentially Lake Michigan, is a huge, it's like a Caddo Lake on steroids. Lake Michigan is a huge example of a Caddo Lake. But a Caddo Lake is a large piece of ice that breaks off. I'll just go ahead and draw it. This is probably something I can draw better than explain. All right. So we have our glacier, big, huge glacier. And so it just advanced, just left by it. That's all its debris and all its chaos and mess and all of that. And so now it starts to retreat. And once again, when it retreats, it doesn't just essentially go back the other direction. It just essentially starts to melt. And so as it melts, it then leaves behind these huge chunks of ice. Now, if these huge chunks of ice were in the ocean, they'd be called icebergs. They'd be something that the Titanic would want to avoid. But because they're on land, they're just big, huge chunks of ice that just kind of, over time, just kind of sit there. And once again, a mile-thick sheet of ice. So you have a huge chunk of ice that's broken off from this Continental Glacier as it started to melt. And so over time, it's going to create a weight. It's going to create a bowl as that weight of all of that ice essentially is going to cause this surface below to start to bow under it. And so what happens in over time is it forms a situation in which it forms this particular kettle-shaped lake. Because eventually what's going to happen is this ice is going to melt and fill its own bowl. So essentially what it is an iceberg broken off from a continental glacier that over time creates a depression and then fills that depression with its own meltwaters. And so throughout northern Indiana we have this particular shape of a kettle lake, which that's supposed to look like a kettle drum, a kettle, those things, I don't know, kettles are even around anymore. So throughout northern Indiana we've got these lakes are kettle lakes. Lake Wawasee, all these scattered through up here are examples of kettle lakes. Essentially ice chunks that are broken off, create a depression, and then fill that depression with its meltwaters. That's what Lake Michigan, that's what all the Great Lakes are. So anytime you see something like this, an image like this, you have to first off determine, is it a sinkhole or is it a kettle lake? And if it's behind a glacier boundary, if it's north of the glacier boundary in the northern hemisphere, you know it's a kettle lake. If it's south, it's probably a sinkhole. So this could be Florida, but it's not because it's somewhere north. In fact, it's from Siberia. So once again, we can see those lakes that popped up all after the Continental Glacier retreat. We already identified that particular pattern. This is up in Lake Wawasee. You can see all these little chunks, all these little lakes that are formed from ice separating and all of that.